Next session is on transport quality and happy eyeballs. And this is a little bit shorter since it's the afternoon, so there's 2 full papers and 1 short paper. And I think Vaibhav, is that how you pronounce your name? Vaibhav is ready to start with the first one. Is somebody going to say what happy eyeballs is? Are you going to say what happy eyeballs is? Okay.
Hello, welcome back.
Can you tilt it a bit?
Yes. So my name is Vaibhav Bajpayee, and I recently graduated with a PhD and from Jacobs University Bremen. And
are you looking for a job?
Yes.
Okay.
That's that was the hint.
Yeah, hints don't work.
Okay. Okay, maybe I can go back. So today I'm going to talk about measuring the effects of happy eyeballs, and this is joint work with Jürgen Schönwalder. Okay. So it all starts with get address info. So this is a function call which is used in Unix-like systems to resolve DNS names to IP endpoints. And what you see in the picture is when you make a request to resolve a domain name using get address info, it will give you a list of endpoints in a particular order that prefers v6. And this is dictated by the destination address selection policy, which is prescribed in RFC 6724. This can also be customized using this configuration file. So what is the issue? The issue is iterating sequentially over these list of endpoints has repercussions. So number one, if you are a dual stack client and your v6 connectivity is broken, the amount of time it takes to fall back to v4 can be in the order of seconds. In fact, there have been studies presented in the IETF already showing that browser connection timeouts can be in the order of 20 seconds, which is fairly visible. Next slide, please. So the IETF thought about this problem and they came up with a solution which helps prevent bad QoE in situations where your v6 is broken. And they call it happy eyeballs. It is defined in RFC 6555. And the idea is very simple. As you see in the picture, you use the first IP endpoint from get address info and make a TCP connection request. Usually it is v6, and you give it 300 milliseconds to succeed. If the connection succeeds in 300 milliseconds, you're good to go. You use v6. Otherwise, instead of waiting for a timeout, you switch to a different address family, which is v4, and then you start a parallel race between both address families and see whosoever wins will be used for the ongoing TCP connection. Bear in mind that the RFC is described with 3 goals in mind. And the number one is to honor the destination address selection policy 6724. The idea is to quickly fall back to v6 to v4 in situations where v6 is broken, and that's why you have this 300 milliseconds timer. And the idea is also to give a fair chance for v6 to succeed, because we want the internet to move towards v6, and that's why the race is handicapped. Okay, just bear in mind these 3 goals because we'll come back to them during the results. Next slide, please. Okay, so what is the issue now? The issue is the happy eyeballs timer value of 300 milliseconds was designed during a time, 2011-12, when v6 brokenness was quite prevalent. And this was largely attributed to failures caused by Teredo and 624. And people have shown, which is 5 and 6, that even in situations where these relays work, transitioning technologies tend to add noticeable latency when compared to native v4 and v6. Okay, so, but we have seen over the years, we are in 2016 now, that these transitioning mechanisms have slowly declined due to efforts made by v6 operations community. If you remember, Microsoft was a huge proponent of Teredo, and Teredo was turned on by default on Windows client machine. They used to use it in Xbox product as well. In 2013, Chris Palmer announced that they will stop Teredo, and they publicly deactivated Teredo servers. And last year, there was an RFC published, which is obsoleting the 624 Anycast prefix. So the recommendation is for future products to not use 624. As a result of all these efforts, the failure rates over V6 have considerably gone down. So these are numbers taken from Jeff's talk from NANOG in January 2016. And what you see is back in 2011, overall V6 failure rate was 40%, and it has gone down to less than 4% last year. Even native V6 failure rates have gone down from 5.3 to around 2%, which is still large, but slowly going down. Okay, next slide, please. So what I'm trying to get to is the V6 landscape has fairly changed today. And this has been due to a large number of events that happened since 2012. First is IANA has completely exhausted its pool of V4 address space, and 4 out of 5 RIRs have also exhausted their pool of V4 address space, as you see in the picture. And there was this massive V6 world launch event in 2012 where ISPs and content providers joined hands to turn on V6 permanently for their customers. And as a result of all of this, we see large V6 broadband rollouts today, particularly by Comcast and Deutsche Telekom in fixed line space, and AT&T, Verizon Wireless, T-Mobile USA in the mobile space. And as a result of all of this, V6 adoption globally has increased to 12%, which is native, with Teredo and 624 at around 0.01%, which were mostly responsible for failure rates. Even Google over IPv6 program, if you remember, this was a whitelisting program where ISPs who wanted V6 from Google had to sign up, and then they started receiving quad A entries towards their resolvers. This whitelisting program has been replaced by Google V6 blacklist. So essentially, you will get quad A entries from Google, but you won't get quad A from Google for certain resolvers where your latency over V6 is 100 milliseconds more consistently than over IPv4. So what I'm trying to get is this landscape is completely different from when the Happy Eyeballs RFC was specified. Next slide, please. So this takes me to my research question. The question is, in this changed landscape, what is the effects of the Happy Eyeballs timer value of 300 milliseconds? And it's largely unclear today. And so as such, we want to know in what percentages of cases Happy Eyeballs is making a bad decision of choosing V6 when it is lower. And in those situations where it is making that bad decision, what is the amount of imposition, particularly in terms of latency, because latency is important today, is happening on clients. And this is particularly important to study because applications on top of TCP will not just apply Happy Eyeballs in situations where V6 is broken, but also in situations where V6 is comparable to V4, right? Okay, so next slide, please. And the effects of this changed landscape you can already see in browser implementations because there is a fragmentation of the timer value in today's implementations. It started with Google Chrome. This was during the time when RFC was being released, and they were using 300 milliseconds. And Safari during that time used to use history of previously witnessed latencies. And starting 2012, Opera and Firefox use parallel TCP connections. We argue that this is not an implementation of Happy Eyeballs because it's not adhering to the V6 upgrade policy or the design goals that I talked about. And in 2015, Apple made a decision of revamping its implementation of Happy Eyeballs, where they still use this previously witnessed latencies, but they give a 25 milliseconds head start to V6, both during DNS resolution and TCP connection establishment. Note that these values are arbitrarily chosen. So the obvious question is, what is the right timer value? And we want to contribute something towards it. So next slide, please. So these are all the contributions that we provide. So we measure, actively measure against Alexa top 10K websites, and we have been doing this for the past 3 years, since 2013, still ongoing. So this has not stopped. And what I show you is TCP connect times over V6 to all these websites have considerably improved over time. We'll look at this. And what we saw is, as of May 2016, which is last month, 18% of websites are faster over V6 with 91% at most 1 millisecond slower. So this is fairly good news for V6 deployment. And HE with the 300 millisecond timer value makes all 99% of these Alexa top 10K websites to prefer V6 98% of the time. So that's a considerable preference towards V6. However, the timer value makes, even though it makes you prefer V6, in 90% of these cases, you are preferring a connection over V6, which is slower than V4. And what we suggest is lowering the timer value to 150 milliseconds will give you the same preference as I show you in 3, but will give you an additional margin benefit of 10%. So you won't choose V6 in situations where it is considerably slower than over V4. For let's take an example where your connection over V6 is going through a continent and not over V4. Okay, next slide, please. So here is some related work. So during the time when HE Happy Eyeballs was being released, a lot of work was done in analyzing the HE implementations. And I'm not going to talk about this because these studies are dated, as I showed in slide 7 that these implementations have changed with time. So these studies do not hold anymore. The relevant work is, which holds today, might be from Sebastian Zander and Jeff Houston, that showed that 75% of the connection attempts towards APNIC from Google Ads, clients that use Google Ads, they prefer V6. And we show in this paper that this preference has increased to 98% today. Okay. We also showed in 2013, which was a V6 of draft, that Happy Eyeballs with 300 milliseconds will never prefer Teredo, which is a good thing because we need Teredo to die. And last year we showed that your YouTube performance over V6 is worse than over V4, but this high timer value of 300 milliseconds makes you prefer connections over V6. So you are actually streaming content over V6, but you can get better performance over V4. Okay, next slide, please. So how do we do all of this? We use a metric. We measure TCP connection establishment time. So it's an active metric, and we have an implementation of this metric. We call it Happy, and it's publicly released with a simplified BSD license. And this is how it looks. It gives you TCP connection establishments to a website on a command line in a CSV format. Two things important to note is it uses get address info, so you will still prefer the endpoints as dictated by RFC 6724, and it will use non-blocking TCP connect calls, and it measures the amount of time it takes for the TCP connect call, system call to complete as a measure of the TCP connection establishment. Note that DNS resolution is not accounted in this because we don't want the latency to be impacted by slow resolvers. Okay, next slide, please. Okay, we measure against Alexa top 10K websites. So these are some websites that we look at. Next slide, please. This is the setup. So the test is ported for the OpenWRT platform, and it is deployed on Samnose probes. So Samnose, if you know, it's a company based in London, which gives out these TP-Link routers to people at home for doing broadband measurements. And we use that platform for doing V6 measurements. And so the test has been running since 2013, and it runs every hour. Next slide, please. Okay, so we had these probes and we gave it to people who had native V6 connectivity at home. And this is the trial consisting of around 80 dual stacked Samnose probes. And most of these probes, as you see in the table, are connected in residential settings. Okay, and thanks to you, some of the people in the room are actually posting this probe from me, so thank you. Side note, I have 2 probes. If you have native V6 at home and you would like to contribute to this work, talk to me, I'll give you the probe. Next slide, please. So let's look at some result. Next slide, please. So this is showing you the trends, the time series of TCP connection establishment times to some popular websites that I consider popular. This is showing you difference in TCP connection establishment time. So 4 minus 6, and this is TCP connection establishment time, again stressing it. And what you if you see anything on the positive axis, it would mean that V6 is faster. And what you generally see is things have considerably improved over time. So let me take an example of Facebook, which is green on the top of the plot. It used during the time of 2013, 2014, used to be 100 milliseconds worse over V6 than over V4, and most of these popular websites over time have become congruent over both address families. So next question that one would ask is, so are these websites faster or slower? And you don't see it in the plot because they have become congruent. So let's look at the next slide. This is showing you the CDF of, again, 4 minus 6 TCP connection establishment time of the past month, May 2016. And what you see is 18, again, anything on the positive axis will always be V6 faster, okay? So for you, it is right hand side. 18% of the websites are faster over V6. 91% are at most 1 millisecond slower. So the plot is extremely zoomed in if you see the scale. And 3% websites are at least 10 milliseconds slower, with 1% at least 100 milliseconds slower. So there is a tail, which is where V6 is actually slower, but large portion of websites which are being hosted by large CDNs, they perform fairly well over V6. Next slide, please. Okay, so then we looked at the entire distribution of TCP connection establishment time. So look at the top plot. Red is V6, blue is V4. And this is showing you the CDF of all the samples that I have in the past 3 years. And what you see is only 1% of these samples ever exceed the 300 milliseconds timer value. So only 1% of the samples matter in this case. So only 1% of the samples are the cases where happy eyeballs will even come into the picture, right? And you can see the effects of this in the bottom plot, where I'm actually showing you the preference of V6 using the 300 milliseconds timer value. And what you see is it gives V4 only 2% chance to succeed to establish a connection. As such, 99% of Alexa top 10K websites prefer V6 98% of the time. Let's next slide, please. Okay, so we know happy eyeballs prefers V6 heavily. So in situations where it does prefer V6 heavily, how does it compare to V4 in terms of latency? So the bottom plot is relative difference, and the top plot is absolute difference. Let's look at the bottom plot, and it's showing you that 90% of the time, happy eyeballs is preferring V6 and in situations where V4 can be faster. Yes, and however, if you look at the top plot, what you see is the absolute difference between V4 and V6 is not that much, right? So in 30% of the cases, V6 is at most 1 millisecond slower. In 7% of the cases, it is at least 10 milliseconds slower. So the difference is not that huge, but still, V6 is being preferred, even though V4 can be a little bit faster. Okay, so then we started asking this question: can we lower the timer value without penalizing the V6 preference? So next slide, please. So the first question one would ask is, why not we just simply disable happy eyeballs today and call it a day, right? If both of them are congruent. So this is the time series showing you a red. Look at the red line in the plot. And this shows you that if you disable happy eyeballs today, the V6 preference will severely get affected. Remember that 18% of Alexa top 10K websites were faster over V6, and that's what you see in the plot. So only around 18% of the time you will prefer V6. And this is not what we want today. So we are still not at the stage where we can disable happy eyeballs entirely. Okay. And this is what actually, coming back to browser implementation, this is what Firefox and Opera do. They do parallel TCP connections, which is essentially 0 milliseconds happy eyeballs timer value. So what I want to encourage here is that V6 still should be given a fair chance to succeed. And that's one of the design goals of happy eyeballs. Next slide, please. Okay, so then what we try to do is we remember 99% of Alexa 10K websites prefer V6 98% of the time. We try to control these two parameters because we don't want V6 preference to go down. We control these parameters and lower down the timer value and try to see until when this precedence holds. Yes, and what you see is around 138 milliseconds it holds, and then it starts to go down. Yes, so I give it some buffer space and say that if you turn down the value to 150 milliseconds, you will still get the same V6 preference as is today, but you will not penalize V4 in situations where it is faster. Okay, and this is what you see in the lower plot. So this is the slowness what you see 4 - 6 in situations where happy eyeballs prefer V6 using the 150 milliseconds timer value, and this time you see 80% of the time it is preferring slower V6, which gives you 10% margin advantage. 10% is huge. Think about it. It's a 3-year long data set, so it's around 18.9 thousand connections. Okay, next slide, please. Okay, so before I go into the conclusion, some limitations of this work is, so the comparison is only comparing against websites over port 80. So I have no clue how it might look like on any other port. And the measurements cover only Alexa top 10K websites. And there might be a tail that might look different. I don't know yet. And the results are definitely biased by the measurement trial, which is heavily centered around US, EU, and Japan. But think about it. The V6 adoption is also centered around these regions only. So yeah, so there is a give and take here. Okay, next slide, please. So this is all what we saw today. We saw that TCP connection establishment times to popular websites have considerably improved over time. So remember the timeline that I showed, things appear to be congruent. And we saw that 18% of Alexa top 10K were faster over V6, while 91% were at most 1 millisecond slower as of May 2016. We saw that with 300 milliseconds, you prefer all 99% of the websites 98% of the time. And the bad news was 300 milliseconds was preferring all these websites, and 90% of these cases V4 was actually faster. So what we try to conclude in this paper is lowering down to 150 milliseconds will give you the same preference as in 3, but will give you some margin benefit of 10%. And that's about from my end. So thank you, and I'm happy to take questions.
It might be off. No?
No.
Oh, there we go. So you showed a time series of basically the data set that you have starting a few years ago up till now with the difference in TCP connection times earlier. Notably, there's a kind of a gap around about, what, October 2015, and then everything seems to be really, really level from there. Like, what changed?
Can we look at the plot again? So there are gaps in the plot, and the gaps mean that there is missing data.
Right, and that's okay, that's fine. I'm kind of wondering what happened to Yahoo.
Yes, I don't know. Maybe you can tell me.
Right, so right, so yeah. So my secondary question there is...
I don't know what happened with Yahoo.
Okay, so my secondary question is, have you retained the actual IP addresses to which you were connecting?
Yes, so...
Because I'm assuming that there are all sorts of factors in play here, either around our CDN footprint or what our DNS load balancing was doing. And if I knew what IP addresses you were hitting, I could probably tell you more.
So the probes are using the same resolver any client would use. So we are not using Google public DNS or anything. So
sure, I'm thinking about what comes back from the resolver.
Exactly. So any client who is sitting at home who is using the SAMNOS probe will also see the same kind of result. Yeah. So the probe is not doing anything special. And yes.
I think Steven is asking if you have the IP address from 3 years ago that you got returned.
Yes, we can talk offline. I can give you the data set. Cool. And for the public audience, I might release the whole data set at some point in time in this year.
Cool. Okay.
If you want the data set, I'm happy to give it to you.
Hi, so that was the second half of my question about the data set. So how did you clean up? So you're looking at V4 and V6. So you're only looking at the top 100K Alexa sites that are dual stack.
10K,
which
yes.
Is, huh?
Top 10K websites.
Top 10K, yeah.
Yes.
Okay. So those tend to be more dual stack than sort of like lower down the edge. But we were doing some stuff with the Alexa top 1,000,000, and we're looking at trying to find dual stack targets, and there was a lot of garbage in the Quad A records. How did you filter out the garbage in the Quad A records?
So what do you mean by garbage?
FE80 addresses. There's a bunch of :1.
Yes. So in that situation, your TCP connection will fail, right? So this is only showing you TCP connections that that succeed. So what
okay, yeah,
right,
got it.
So this is not garbage.
So well, no, because the problem. Okay, so yeah, then basically ones where you have just a garbage address for V6, the happy eyeballs is going to do you're just going to have a happy eyeballs delay then.
Yes, Brian. So I see your point. I also think so. In Alexa 1,000,000, there are around for general audience, there are around 60K websites which are dual stacked, and I suspect that most of the websites in the long tail will even fail to establish the TCP connection. So that's what you mean by garbage, and I agree with you.
Yeah.
And that's why I think it will not bias the happy eyeballs timer.
I don't think it biases the happy eyeballs timer. I'm just trying to figure out what it would look like in this data. So we can take that offline, because so out of that 60K in the top 1,000,000, like 6K had issues.
Yes,
when we
so
looked at it.
there will be. I suspect there will be higher failure rates in the long tail.
But in the long tail, definitely.
Yes.
Yep. Cool. Thanks.
Hi, Aaron Falk, Akamai, and I just want to point out that I went and looked up and found some public information from 2014 that shows that Alexa Top K, almost all are using CDNs, and at least in 2014, about half are using Akamai. And so your population, you have a large number of domain names, but actually it's a very small set of infrastructure. Akamai allows the content customers to separately choose whether their origins are IPv6 available or whether Akamai is serving v6 to end users. And so they can, a content customer can come in, not upgrade their origin at all, and then allow v6 traffic to go to the end user, and that's in their control as well. And so while the infrastructure may be capable of serving v4 or v6, any particular website, it's up to the customer whether they decide that they want to allow v6 traffic. And this is largely because people weren't totally comfortable with it for a while. And now it's picking up steam and it's becoming a little bit more of an expected thing that you should be able to support as more end systems are having native v6 support. So just wanted to point that out, and it might be interesting if you were continuing to look at this data to do a slice that was maybe sort of a unique unique IPs isn't going to give you the right answer because the CDNs, many IPs are shared. But if there was a way of sort of sorting out CDN traffic versus non-CDN traffic, so you really did get a sense of the percentage of sort of operating systems that are being made v6 available, so you get a sense of, because I think that it's going to be heavily skewed towards these CDNs, which have all sort of common infrastructure.
Right. So before you leave, can we go to the methodology? It's before blah 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 blah. Yes. 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 So paper 13, we already did that. The paper 13 is showing you within the Alexa websites where are these websites hosted. So what does the CDN clusters for v4 and v6 look like? And they look different, but it's largely driven by Akamai and Google. And so what you say is entirely correct. But we also have to agree to the fact that that's the world we live in, right? Popular websites will be hosted by CDNs. So I'm not sure that there might be value in actually separating this out, because I want to see the quality of experience of a user, and user is going to popular websites, and these websites are served by CDNs. So I want to see what is the latency that you see hitting those CDNs, and not specifically some skewed website which is not hosted by a CDN, right? So,
true, but embedded in your logic is that you've got this large number of websites, and it's very hard to, it's sort of a black box that isn't very changeable because of the number of them. But for things like large CDNs, if you know what the right answer is, or there's some improvement in the behavior, you can affect that side if it makes sense. So I totally agree with your statement, but where you're trying to get to is, this is what the way v4 and v6 are performing today. Well, those things can be improved. A small number of actors can make large scale changes. I guess that's what I'm trying to say.
So one thing that I can hint out from the paper 13 was what we saw was, we did the study in 2014 and paper got published in 2015. What we saw was most of the content that we were getting for popular websites was being hit by Akamai caches or any other large CDN cache over v4, but not over v6. And that's what was creating a diversion of latency between v4 and v6. But this might have changed with time, because that's what we see. Things look congruent over v4, v6. So it's possible the caches are now becoming dual stack.
Cool. Well, nice work.
Good.
Thank you.
Thank you. Remember, he's looking for a job. All right. Second paper in the Happy Eyeball section is on the cost of using Happy Eyeballs for transfer protocol selection. Anna.
Yes. That doesn't work. Yeah, it doesn't work to advance the slides.
It doesn't work.
You need to tell me to change the slides.
Yeah. I got it for the pointer one.
Sure.
Okay, so hello everyone. So I'm Anna Brunström from Karlstad University, and here to present the paper on the cost of using happy eyeballs for transport protocol selection. And this is joint work with a number of my colleagues in the NEAT EU project. And in particular, Georgios, the first author, is the one that has carried out the measurements that I will be showing you today. So next slide. So we all know that it's quite difficult today to deploy a new transport protocol over the internet. And we talk about ossification of the transport stack and how to get new protocols out there. And one of the problems that we have to face if we want to deploy a new protocol is how do we know if it actually works end-to-end over the path? And unless we have some explicit signaling or a priori knowledge of this particular path, the only way we can really find out is to try it out. And we have to make sure that it's supported both by the other end host, but also that it can go over the path so that the various middle boxes that you have along the path does not prohibit you from communicating. So if the new protocol doesn't work, then we also have to have some fallback mechanisms so that we fall back to some other protocol that can be supported over the path. So this is the background that brings us to transport layer happy eyeballs, or using happy eyeballs for transport protocol selection. So we already heard from the previous speaker about using happy eyeballs for selecting between IPv6 and IPv4. But this is a case where you could also have it useful for selecting a transport protocol. So next slide, please. So to illustrate how this works, so we here have an example with TCP and SCTP and using happy eyeballs to select the protocol. So we would then initiate both the TCP connection and the SCTP association at the same time. And then when the packets come back, in this case, the TCP SYNAC comes back first. But we here have a preference for using SCTP. So we have some delay similar to what was talked about in the previous presentation, where we had some delay to prefer IPv6. In this example, we have some delay to prefer SCTP, and the SCTP init ACK comes back within this time delay. So we can close the TCP connection that we no longer need, and we can then continue to use SCTP over the communication. Next slide. So this was the basics of how happy eyeballs for transport protocol selection works. And of course, happy eyeballs is not something that we have come up with. We already have the whole presentation about how it's used for selection of between IPv6 and IPv4. It has also been proposed in the past for using SCTP over HTTP, or sending HTTP over SCTP, I should say. So there were a number of drafts suggesting this in the past. And now, of course, we have the ongoing work in the transport services working group within the IETF that aim to define a number of transport services so that applications can connect to a transport service rather than to a protocol. And as part of the work within that group, it's then needed to explain how to select and engage a protocol and how to find out what protocol is actually supported between a pair of endpoints. So this, of course, calls for some type of happy eyeballs mechanism. Next slide, please. So hopefully you now understand how happy eyeballs for transport protocol selection would work, and also that this could be useful mechanism to help the deployment of new protocols. So what is then the cost of this? Well, typically good things come at a cost, right? So if you're now going to use happy eyeballs, this is also going to mean that we send multiple requests in parallel. So you will have an added load on the servers, both in terms of the CPU and the memory usage, and of course also an increase in the network traffic. So the goal of the paper that I'm presenting here is to look at this cost, and particularly from the server perspective, examining what is the cost of happy eyeballs from the server side. Next slide, please. So in order to investigate this, we have set up some experiments. So the setup is quite simple. We have a web server that supports both SCTP and TCP. And then we have a web test client that initiates the parallel connection requests over TCP and SCTP, and then selects one of them for the communication. We have a network emulator in between, and in this case, we're just using it to introduce a basic delay of 20 milliseconds in the communication. We execute each of the test runs for 10 minutes and then use a varying load in the test, so between 100 requests per second and 1,000 requests per second. And the metrics that we have looked at is both the CPU load and the memory usage. Next slide, please. So we looked at 3 different scenarios of varying complexity and realism, perhaps. So the very first basic test case scenario is a scenario where we use no caching, so we don't learn anything from our previous connection attempt. So every time we start a new connection, we will start both a TCP and an SCTP connection, and all the connections are unencrypted. And in this case, TCP is the one that always gets selected. Next slide. So this is the first set of results. So on the y-axis, you have the CPU utilization. On the x-axis, you have groups of experiments here for the different average request rates, running from 100 requests per second up to 1,000 requests per second. And you have 3 sets of bars for each one. So the first one is the situation where you send the request over just TCP, so a single setup over TCP. The second one is a single setup over SCTP. And the third one is the one with happy eyeballs, where you always send 2 connections, and TCP is the selected protocol. So if we look at this, we also have a red and a blue bar. And the blue bar, then the object that we download from the web server is 1 kilobyte, and in the red bar, it's 35 kilobytes. So in the case where you have a 1 kilobyte download, and this simple case, it's kind of the worst case scenario, because you always try 2 connections, and you have you basically just have 1 packet that you need to download the whole object. So it's very light load on the server side. So if we look at the results, we can start and we can look at 1,000 requests per second, because it's easiest to see here. If we start at looking at the blue bar first with the 1 kilobyte request size, you can see that the CPU load increases quite significantly when you use TCP or when you use the happy eyeballs TCP in parallel. We can see that SCTP has a bit higher load compared to TCP. So this is why we have these steps here. Already, if we look at the red bars, the 35K situation, we see that if we compare the SCTP and the happy eyeballs TCP, there is not so big of a difference anymore. And the reason is that you now have a larger object, so you also amortize the cost of the happy eyeballs over a bit larger connection. So it's quite natural. Next slide, please. So on this slide, we have the memory usage. So on the y-axis now is the kernel memory usage. On the x-axis, we have the same things as in the previous graph, the different loads, and the 3 situations with TCP, SCTP, or happy eyeballs TCP. We can see, as compared to the CPU load, the impact of memory already in this very basic test case is quite limited. We don't see a big difference between the pure TCP or the happy eyeballs TCP, and we can see that similar to the CPU load, SCTP consumes a bit more memory. So actually using SCTP consumes more memory than the happy eyeballs that results in a TCP connection. Next slide. So this was the results for the first scenario, the very basic test case. In the second test case, we have the same setup, but the connections are now using TLS encryption. So we're still using happy eyeballs for all of the connections. There is no caching, no learning in the process, but the connections are encrypted. Next slide. So looking at the same set with the CPU utilization, we can see that the difference between the protocols are now much smaller. So the cost from going to TCP to the happy eyeballs TCP is smaller also for the smaller objects. And the reason for this, of course, is that the TLS encryption is now adding a lot of a constant cost here that is encountered whether you use happy eyeballs or not. I don't know if you saw the numbers, but in the basic test case, The cost over here was about 6% in CPU utilization, where in this case we're about 25% CPU utilization. So there's a big difference when you add the encryption here. Next slide. This further illustrates the point. So this is breaking down where the CPU load is encountered for the case without TLS and the case with TLS. And the main point to note here is that this light gray part, which is the time that the web server spends in user space processing, is a very big part when you add the TLS, because this is where the encryption part comes in. So we see that this is dominating the cost here, much more than the happy eyeballs. This is again showing the memory usage for the TLS test case. As for the base case, we see very little impact from happy eyeballs, and SCTP is still having a higher cost than the TCP version. Okay, next slide. So then in the final test case, we now added some caching, because of course, if you were to use this happy eyeball mechanism in practice, you would like to learn from your previous connection attempts. You wouldn't always try everything. So you would actually cache some knowledge for how your previous connection went, if the protocols were supported or not. So we now added caching to both the unencrypted and the TLS encrypted scenario. And we also added different outcomes for the happy eyeballs process. So in the previous results, it was always TCP that was selected as the winner. So in this case, we have TCP always being the winner, or SCTP always being the winner, or a 50% chance of either of the protocols. So half of the times you get the TCP connection, and the other half of the time you get the SCTP connection. And this is the outcome of this scenario. These legends are hard to see, I guess, but I will talk you through it. So we still have the CPU utilization on the y-axis, but on the x-axis, we no longer have the load. Now we instead have the cache hit rate. So over here, it's a cache hit rate of 0, so you always try both protocols. And over here, it's a cache hit rate of 1. And the cache is populated with TCP in this case. So with the case of 1 here, it's a TCP connection selected immediately. And then we have the 3 bars. So the first one is when the happy eyeball selects TCP. The second one, when happy eyeball selects 50% of the case, either of the protocols. And the third one is happy eyeballs selecting SCTP. And for the unencrypted and the encrypted case, and the different object sizes. So if we see down here, we see the outcome of the happy eyeballs mechanism, having the difference between TCP and SCTP that we saw in the previous slides. But the main point to note here, of course, is that once you add caching, it's no surprise, this is going to reduce the load on the server. So you see a gradual decrease, and this effect is largest for the unencrypted scenario, because this was where the cost of happy eyeball was the largest to start with. So of course there we save more by applying caching. For the scenario with the TLS encryption, we had a smaller impact from the beginning, but we still see that we have some gain from applying the caching also in this case. Okay, next slide, please. So to summarize, we have seen that the low increase in the CPU utilization was quite limited for these initial performance evaluations. So even in the most basic scenario for the 35 kilobyte object sizes, the increase as compared to using SCTP was less than 10%. Then if you have encrypted connections, this is going to dominate your CPU load and have a much bigger impact than the happy eyeball mechanism itself. And of course, if you add caching, this is going to save you even more on the CPU load. So it's quite a small increase actually when you add all these different components. And for the memory usage, we don't see much impact at all. So taken together, I think the results indicate that from the server perspective, it's quite feasible to apply transport layer happy eyeballs for selecting the protocol. Next slide. So for continuing, this was some first very basic measurements. So of course we want to extend the measurements and also look at some more complex scenarios where you have maybe additional protocols and also combining it with diversity at the IP level with IPv6 and IPv4. This work is part of an ongoing work to build a transport system that allows applications to select transport services rather than specific protocols, and then have the machinery to provide the selection. And having happy eyeballs implemented in that, we of course also want to make some real measurements over networks to see how this interacts with middle boxes and other pieces in the network. And of course also bring the pieces back to the TAPS working group. Okay, thank you.
Questions?
Hello, Vaibhav Vajpayee, Jacobson University, Bremen. So I am wondering, in addition to CPU and memory usage, wouldn't it be nice to also study how much of the network traffic actually doubles as a result of happy eyeballs? So in what percentage of cases we had to send a second packet in addition to double the traffic? Because that's what CDNs, like network providers, care about, right?
Sure, so you have two aspects here. So this only considered the server load. And the reason we started there was also because this is a bit more specific for the transport case as compared to the IPv4, IPv6, as here you create the state in the servers for trying different protocols. For the basic scenario here, it's of course quite easy to calculate exactly how much extra traffic is generated because we know how many attempts that send the extra packets. But sure, that's an aspect that was not covered here.
Olivier Bonaventure, you showed in your measurements the CPU load when you had 1,000 requests per second. Have you looked at what's the highest load that you could sustain on the server side?
No, we have not. So this may, of course, be different depending on how the load is affected. So the way we measured it here was that we sampled the load every 20 seconds during the run to get the average load from the different mechanisms, but we have not looked at when it saturates and breaks down.
Because the numbers might be different for regular connections and MPA cables. Thanks.
Yeah, so that would also be a good addition to look at. So in general, measuring this accurately is not so easy. So Georgios, who did the measurements, he was trying a lot of different tweaks to try and get these numbers in a reliable fashion.
All right, thank you.
Okay, thank you.
And the last one is a short paper. Start me up. Determining and sharing TCP's initial congestion window. We're going back to the 5-minute game here. No, hang on. It's coming, it's there.
Hi everyone, my name is Shafiqul and I'm going to present on Start Me Up, determining and sharing TCP's initial congestion window. Next slide, please. Before delving into the details, why are we doing this? As we know, each TCP connection maintains states in a data structure we call TCP control block, TCB. And sharing this TCB across parallel connections and combining their congestion controllers can be beneficial. Very beneficial when flows are short. It can reduce the flow completion time, and the flows can skip slow start by immediately taking the large congestion window. Plus, we can also apply prioritization among the flows. But there is a key problem. Do parallel connections follow the same route? We have a draft where we mention everything about that, so you can take a look, but I will focus on the main part of this paper. Next slide, please. So the problem, if we don't, if a short flow joining an aggregate take a large initial window, it can create burst in the network, which can lead to more queue growth and losses. We show this problem by using our implemented coupled congestion control in NS2. And as you can see, the red line, connection 2 joining after 5 seconds, basically bursting in the network. And next slide, please. And the solution is obvious. We have to pace the packets. So prior approaches, they have used some kind of timer-based solutions for pacing. Here, our approach is simple, and we propose to maintain the ACT clock of TCP connections. As you can see, the graph below is basically that when the connection 2 joins after 5 seconds, it actually uses the ACT clock of connection 1 to clock out the packet transmission over the course of 1 RTT. And similarly, when the connection 3 joins, it actually uses the ACT clock of connection 2 and connection 1 to clock the packet transmission. In that way, we don't have to change the dynamics, and we can easily use and maintain the ACT clock of the TCP connection. Next slide, please. And to show the benefit that it actually reduces the flow completion time, we ran a simulation with a long flow and a short flow. Short flow joining after some time actually finishes up very quickly. The pink line actually, following the Y2 axis, shows that with our proposed ACT clock mechanism, the reduction of the short flow is 40% or above for when the capacity grows, for as long as there is enough capacity. And it's even better than the red line where there is no ACT clock mechanism. That's all, but if you're interested to hear more about this, I'll be standing right over there. Thank you.
All right. You guys are keeping excellent time. We are 10 minutes ahead of schedule. So I think the plan now is to run without a break into the next session and then have a... You got a break there. I don't think I have a break on the webpage.
The break?
Colin wants a break. No, I think our timings are slightly different here. Let's stick with the webpage. All right, so we're running straight into the next session, and then we have a longer poster session again of an hour at around 3 o'clock. Next session is measurement, and we have 1 full paper and 4 short papers. Daniel is going to have the first paper on revisiting benchmarking methodology for interconnected devices. And get coffee and ask questions. You were way more active in the morning.
Hello, I'm Daniel Raumer from TU Munich. First of all, I want to say some background. This work is the converged output of a discussion of numerous authors. So you will see we have a lot of points to discuss at benchmarking methodology. My outline is as follows. First, I will say a few words about our case study we performed about benchmarking routers, which are called interconnect devices according to the famous RFC that defines that. And then I will present selected examples that show flaws in the current best practice in benchmarking. And I will derive some conclusions and propose some things that we can improve or we think we can improve. First of all, why should we revisit a benchmark, the methodology that was established decades ago? So currently, there is some divergence of benchmarks because this RFC has been proposed some decades ago, and the best practice has evolved. So there are updates, there are considerations, there are extensions also by other organizations than the IRTF, and also there are quasi-standards established by the vendors of devices for benchmarking. And then there's the new class of devices that me and my colleagues are especially concerned with, which are software devices. So it is about devices that run on CPUs, have caches, and perform network packet processing on the CPU. So, for instance, examples are high-speed network I/O frameworks and virtual switching. So the common metrics from best practice benchmarking that are defined in RFC 2544 are throughput, which is defined as the highest rate a device under test can serve without packet drops. Then there is the back-to-back frame burst size. To determine that, you send as many packets or frames back-to-back, and then look at the longest duration a device under test can serve such a burst without any drops. Then there's the frame loss. Oops, sorry. The frame loss rate. It's the percentage of dropped frames under a given load. And there's latency, which is the average duration that a packet needs to pass a device under test. A lot of extended metrics based on those exist. For instance, if you want to determine the performance of your routing table. And there are, as I mentioned, additional shoulds and extensions, but most of them are rarely measured if someone presents a benchmarking report of a device under test. So typical setup of such a benchmarking set is you have a benchmarking test suite. So in our case, in our setup, it's an RFC 2544 test, and the terminology is device under test for any device you connect. In our case study, we used a Linux router, a FreeBSD router, and a MikroTik router. Especially the MikroTik router, it's a hardware box you can buy, and the special thing is outside it looks like any other switch or router for a server rack, but internally it just does everything on a CPU. And to determine the metrics I mentioned, you have to configure some loop inside the device under test, and then you can send traffic through and perform latency measurements. So now that I've explained the setup, I want to dive into the selected examples that I mentioned. The first of all is the current best practice is to just measure latency by determining the average. So I selected the example of the FreeBSD router, but I could also have selected the example of the Linux router, for instance. And the average would be this. So we have it would be a value of 7. And if I look at the histogram, which shows me the complete distribution of all latencies that I've measured, I see there's a long tail that is actually not reflected by average. So in this case, average may be okay, but if I go to an extremer example, what happens also in some devices, if packets have to travel through different paths in the device, I get some multimodal distributions, and in that case, the average seems to be ridiculous. So the example or our proposed solution is here for visualization, of course, use histograms. But in a benchmarking report, you want to have values that are comparable. And in that case, we propose to use percentiles and especially 25s, 5s, 75s, and some percentiles we propose as worst case. Okay. The next flaw I want to discuss is, okay, first I have to explain the graph. If we, the benchmarking standard determines we should measure the latency under the maximum throughput load. So if I look at the graph where I increased the load on the x-axis, and the latency is plotted on the y-axis, that would be this point here at the end, shortly before the system is overloaded. And this example is a software open vSwitch running on a commodity server. And due to some effects of Linux, NAPI, and the network driver, we get the best latency at that point. So now it does not really make sense to measure the latency at that point and consider it as worst case latency. So we propose to do latency measurements at each measuring point in our benchmark. So also at lower loads, which maybe perform worse or have higher latencies, especially on software devices. So the third example is the same graph I showed, but with a different traffic pattern. So instead of CBR, which is considered to be the default traffic for benchmarking, that means constant bitrate traffic, we use Poisson traffic, which rather can be considered more realistic. And in that case, we do not see that strange effect. So our statement here clearly is, please try also to use other traffic patterns. That is something that is a should in best practice, but we did not find any benchmarking reports in the wild that used other traffic than CBR traffic. We can have, why did we use Poisson traffic? That has further reasons. So another reason is for traffic generation, you often want to combine different sources of traffic. If you combine two CBR traffics, you do not get any CBR traffic. But if you combine Poisson traffic, you again get a Poisson traffic. So this traffic also has some other beneficial points. Then I mentioned for device benchmarking, there are state-of-the-art tests, and then there are additional tests. Some state-of-the-art tests do not reveal too much insight. And this is an example for an additional test that reveals insight, but is usually not performed in benchmarking reports of devices. So in that case, what do we see? It's on the x-axis, we increased the number of routing table entries inside a Linux router, and the blue line determines the achieved packet rate, the maximum throughput in terms of million packets per second. And especially for software devices that have, as I mentioned, the caches of the CPU, we get the grading points at each time that a cache is exceeded. So what we can see here is the exceeded line of the layer 2 cache, which is plotted as red, because we additionally, for explanation, added it. It's the red graph, and the cache misses went up at the point when the performance decreases here. And the same happens for the next cache layer. So the statement of that graph is the caches affect the performance, and therefore we need to test further configurations and routing table sizes, or more general, further lookup table sizes. Therefore, we need, for certain classes of devices, we need additional tests and functionality dependent tests. Another issue that we had is reproducing tests. So we had RFC tests seen, benchmarking reports, and we had problems to reproduce them. That mainly is an effect that gets worse with software devices, because if software devices get updated, perhaps the performance may change. So with having more software in a system, there's more complexity and more chances to change any configuration. And if that configuration is not documented, it's hard to reproduce a result. So the main reason for that is device configuration is often done manual, and that is error-prone and less documented. So we propose that each benchmarking setup should be configured automatically by a script, and that script can be given to reproduce the result of the benchmark or to see what was the exact configuration of a benchmark. And in our case study, we have solved that problem by doing some automatic configuration of the devices. So that brings me to my conclusion. Especially the novel classes of devices, of software devices, require that we reconsider benchmarking best practice that has been established decades ago. Then my points that I pointed out, but there are more in the paper. Average latency is, of course, in a lot of cases misleading, and we propose to use histograms and percentiles. Then latency measurements should be performed at each packet rate that we stress or use to stress the system, and CVR traffic is not sufficient, so at least there should be used a second traffic pattern, which is Poisson traffic that we propose. And then software devices have a lot of device-specific performance, and these performance issues, and these issues should be considered with the additional tests to also be covered. And the last point I mentioned was the manual configuration. Then I'm not totally finished, because there was another novelty about our case study that we performed. About the case study we performed, we did this as we not just benchmarked software devices, but we also used a software device that runs on commodity hardware to benchmark our devices. We did this with Moongan, which was not a novel thing in the paper here, but it was published last year in a paper. And Moongan is able to use hardware assist of network cards. To mention, we can do the exact latency measurements by misusing the precision time protocol feature that network cards support, and then we get precision at about less than 10 nanoseconds. And Moongan has some other clever tricks, for instance, to really produce exact traffic patterns that really work. And other software packet generators fail there. So we can benchmark software on commodity hardware with software on commodity hardware. So if you want to try what we did, the framework is publicly available. We published the reports also on our website to have a look at the reports that already include the histograms, which are beyond the current best practice. And you can try it out by going on that website. So that was it.
Thank you.
Matt Ford, thanks. That was an interesting talk. I was wondering if this work has been presented to or developed at the benchmarking working group in the IETF. So I took a look at the agenda for this week, and I see that it says that You might be giving this talk there if you're available and there's time on the agenda. Will you be available? Because I think
I see Martin is
it would
already
be,
coming. So
it would be
yes,
great to make time for
it's
this
the
talk on
plan
the
to-
BMWG meeting this week. So are you going to, are you
it's the
available?
plan to present it.
You are
Yeah,
planning.
sure.
Great.
Dave Tott, and I also am looking for a job. Thank you for pointing out MoonGen. I wanted to also, pointing out the multimodal distributions of latency is a real thing, and averages are typically meaningless in that case. I did have your suggestion that we enhance CBR measurements using Poisson. I would, given a choice between those two alternatives, I'd actually rather be benchmarking TCP, which has a significantly different behavior.
So Dave, just to follow up on that, Al Morton, you mean bursty traffic. And yeah, I gotta fix this. All right, now it's Al Morton's size. So I was thinking the same thing about the traffic. If we go back to what our performance measurement forefathers said here in IETF, the Poisson distribution is probably a decent distribution for session arrival, but not for the interpacket distribution necessarily. They're sort of shooting for like an unbiased view. I think it's good to show that Poisson is obviously different from CBR, and the performance you collect as a result is different from CBR. But then if you really want to claim something that's real world, now we've got to go to session and burstiness and adding more things like that. And model-based metrics draft without the flow control of TCP tries to get at exactly that problem. So there's some cross insemination that we can do between IPPM and benchmarking if we really want to attack this traffic distribution realism point. But now on to my question. So here we go. You mentioned repeatability and the automation of testing. And one of the ways that test equipment up till today has attacked the problem of determining this throughput level, which for background is the maximum offered load at which you measure zero packet loss. There's been multiple ways to attack this problem, kind of a binary search where you go above and below and try to get close in the damping. Other folks have done this linearly from above and linearly from below. These are all viable ways to search, but so actually the searching has some variables in it, and you'll get different results depending on that. And everyone has always used some sort of resolution. In other words, I think I'm close enough and I'm going to stop testing now. I'm not trying to get down to the resolution of 1 packet per second kinds of things. I'm just trying to get close in some resolution. And I'll also mention that some folks even put resolution around what is zero. Zero is some places past the decimal point, at which I'll accept some packet loss. That's not what Scott Bradner envisioned way back in 2544. So in MoonGen, what search algorithms do you use, and did you try some different ones, and how did that affect your repeatability?
So we did both. We did linear searching from lowest rate to highest rate. We did sometimes we stop if we have the maximum rate, if we automated that, and we also had tries with binary search. The problem of binary search is if we want to plot nice graphs, at the end we have to perform the test again with a linear search. So for other reason that we need the data for different plots, we use linear search, and if we really want to do it fast, we use a binary search.
Well, it seems like if you reordered the data, you'd get your linear plot to some degree. But you also make the point that you want to measure. I'm not pointing at anything in particular. You also make the point that you want to make these latency measurements at less than 100% throughput level. So that's actually that's some reason for why you would want to do both the linear from below and the binary search.
So yeah, that would be a drawback, that tests can increase in time if we propose to do latency at each percent of maximum throughput rate. Definitely.
So it's really cool that you've adopted and are now trying to improve on the IETF RFCs in this area. And of course, the big improvement here is that it's not $1 million piece of test equipment. Sorry, ICSI and Sparing.
Yeah, so thank you.
All right.
Are there any questions?
Any more questions? No? Okay, thank you.
So Colin and I decided we're going to stick to neither of the agendas that we had, and we are going to take a break now. Please be back here at 2:35, so in 17 minutes.
We decided the short paper presenters need caffeine so they speed up.